All right, let's continue with this practice test and the solution. So here's number 2, which is a doozy of a question. So you have a rational function, right? We talked a lot about these. And so these functions afford us the opportunity to talk about both limits and continuity. So here are a couple little leading questions, right? And so I'm going to start over here, and I'm going to write that they're equal, but they really aren't, quote unquote, equal. They're almost equal. So that's kind of like when I simplify, all right? When I pull an x out of upstairs and downstairs, you get x plus 2. Okay, and again, they're not really equal, but they're almost equal. In fact, we would say that these two functions agree at all but one point. Okay, so with that said, let's take a look at what the limit as x is going to 0 is. Well, why don't we just use our easier function to evaluate that limit? It's the same thing, certainly around any point. The only place they differ is at 0. So we're going to use that easier function, to examine the behavior of our original function around 0. And so now all I have to do is substitute, plug a 0 in, and of course I get 1/2. All right? Okay. When we try to evaluate this particular limit, it's not going to exist. Right? In fact, what we'll really get is plus or minus infinity, which we can see by the graph, which we'll pull up in a hot second. So that's actually going to equal plus or minus infinity, which therefore means it does not exist. Okay? Now, note that you can get rid of the factor of x, which means you can ultimately substitute 0 after factoring, right? Which means x equals 0 is removable algebraically. You cannot get rid of the x plus 2. Therefore, x equals -2 is non-removable, right? So let's get more into that right now. So there are two discontinuities, okay? And here's one of them, okay? X equals, we'll start with 0, is certainly a POD. Why? Well, f of 0 just does not exist there, right? You can't plug 0 in. I don't care about this function. The only difference between these two is at 0. At 0, there ain't nothing going on here. Okay, at 0 here, it's fine. 1/2 is the y value. Okay, so for the function which I'm thinking about, this one, right, f of 0 does not exist, right? Well, what type it is? Well, it's removable. It is removable since the limit exists. And actually, I should write, well, I'll be a little lazy here. Right, because I already showed the limit as x is going to 0 is 1/2, right? And that's what it means to be removable. In calculus terms, there is a limit. Okay, in algebra terms, you can get rid of that factor x over x, which means 0 can then go in. Okay, there's one more POD, it's -2, right? Why? That's right, f of -2 doesn't exist. Right? You can't plug -2 in here. Give you 0 over, give you indeterminate form. Actually, you can just give you something over 0, not indeterminate. So what we have for that particular case is that it's in fact an infinite discontinuity. Infinite discontinuity. And I already showed you why, right? Because the limit as x is going to -2 is plus or minus infinity. And I'll say is, quote unquote, plus or minus infinity. Bad notation, plus or minus. Right? So bad notation, but you have the notation up here you can reference. Okay? Now, if I were to graph this, let's take a look at what the graph looks like of the function, which I will ask you to do. So here's a graph. I took the liberty of putting it in earlier. Remember, it's x over the quantity, everything in the denominator in parentheses. So I'm going to graph her up. Now remember that, and I'm going to actually get a better window. We'll go -5 to 5. We don't even need that much. How about that? So there are 2 points of concern, right? One is here, at 0, right? So what this graph is not showing you is that 0, there's a hole. There's a removable point of discontinuity. right? The limit as x is going to 0 is 1/2. So if there were a value, which there isn't at 0, it ought to be 1/2, right? Which is the limit as x is approaching 0, right? As x is going to 0 from both directions, we're heading towards 1/2. Okay? So there is a hole here, right? And when x is 0. There's a vertical asymptote, your other discontinuity, when x is -2. Okay? Hole, vertical asymptote, done. All right? Okay, moving onward. This problem we've done a lot. I'm going to move on with that one. Okay? And let's take a look at number 4, because that's kind of fun. Right, so number 4 is kind of asking us to think about the function, right? And maybe I'll draw this one. That might work a little better. And so I'm going to kind of get a little pen action going. Right, and let's think about what this function might look like. Right, so I'll draw it first and then we'll get more specific. So it looks like e to the x, which is exponential. So e to the x looks like this. Right, that goes through 0, 1, but it gets bumped up 3, right? So instead of going through 0, 1, it's really going through 0, 4. Okay, but that's what the function looks like really to the left of 0, right? So really what I need to show is that e to the x is going to look like this. Right, but it's going to go through the open, actually x is strictly less than 0. We have an open circle at 0, 4, right? So that's e to the x plus 3, right? Now to the right, it looks like 2x, which is a line with slope 2, plus some intercept, right? But I want that to come in right here, right? I want this merging point, this pivot point, I want them to connect at the same y value of 4, right? So how would I write that? Well, here's how I could write it, okay? Let me write. Maybe I'll write it by hand. Okay, I'll write it by hand. So the way I'd write this problem is as follows, right? In order to be continuous at A, here's what I want, right? I want the left-hand limit to equal the right-hand limit, right? So the left-hand limit has to equal the right-hand limit in order to have A, a limit at all existing, and B, therefore continuity, right? So everything I would like to happen, I want both of those limits to be 4, which also happens to be f of 0. Okay, so I want the left-hand, right-hand limit to be 0. The limit as x is going to 0 from the left, we're going to use the left piece, which is e to the x plus 3, right? That's where what the function looks like to the left of 0. So I'm going to use e to the x plus 3. I'm going to substitute, bam, right? That's where I'm getting the 4 from, right? It's the left-hand limit, okay? The right-hand limit, therefore, I need to be 4. So the limit as x is going to 0 from the right, here's our right-hand limit. And to the right of 0, I'm going to use the line, 2x plus a. So I need that to be equal to 4, the same 4, which is the left-hand limit. Okay? So that means that 2 times 0 plus a by substitution has to be 4. Right? And therefore that means that a equals 4. Okay? So now if a is 4, I have continuity, at least the limit works out. Left and right hand, and therefore I have continuity. Okay? So now, to summarize, that would mean f of 0, which is e to the 0 plus 3, which is 4, will now also be the limit of both pieces of my function as x is approaching 0, right? And that's what it means to be continuous at a point, right? F of 0 equals, whoops, where did that limit go? Oh my, I'll do this again. So the f of 0 is 4, right? It's e to the 0 plus 3, which is 4. And so now that's equal to both left and right hand limits, which is the limit as x goes to 0. Okay? And isn't this what it means to be continuous at a point? Right? When the behavior at 0 is equal to the limit as x is approaching 0. Both of which, in this case, will be 4. Okay? All right, more to follow. Keep working.